Hey everyone, welcome to my YouTube channel, Physics for Pedestrian, and I am going to talk about this problem number 71, which is part of the series of problems on quantum mechanics. So let us start with this very beautiful problem, which says that Hamiltonian due to the interaction of a particle m, particle of mass m and charge q and spin s, with a magnetic field pointing along the z-axis is h cap equals to minus of qb divided by mc s cap z. Right? So the Heisenberg equation of motion for the time-dependent spin operator s cap xt can be written as. So basically it is asked, so how it can be written as. So let us try to understand this problem. So it says that everything is given here, and it is asked that you have to find a Heisenberg equation of motion for x component of spin angular momentum and its time evolution, basically time, how it evolves with the time, right? So let us write the Heisenberg's equation of motion, which says that for any operator A, it can be written as dA by dt equals to del A by del t plus commutator of A with Hamiltonian H. Right? Now remember that this is mostly zero because operator doesn't explicitly depend on time. No explicit dependence of time. Right? Now this type of problems are very frequently asked in most of the exams. So we need to understand it thoroughly. So let us take this operator S here and just try to solve it using this formula. So d x cap t is nothing but where A is, remember that Sx, T and H, right? So just remove this thing, and it is clear that it is a part of no explicit dependence on time, rather than it has implicit dependence. Right? So this is nothing but, just try to solve it. Now here, and obviously there is 1 by I h cut. Is there 1 by I h cut. Right? Now what is this Sxt? It's nothing but 1 by I h cut. It can be written as e to the power I h t s naught e to the power I h t h. But remember that this is how an operator evolves with the time, right? So this is S0 is nothing but an operator at a time t equals to 0. T equals to 0, and this is how it evolves. But remember that these evolution terms are they simply commute with h, as both are same operators, so they will be simply taken out. So what you are left with is basically s naught and h. Other things as out. So let us try to simplify it and write this step here, which says that d Sxt divided by dt equals to 1 by I h cut into e to the power I h t into, this is s naught x, obviously, s naught x h and e to the power minus of, sorry, here minus of I h t, right? So this is what is S naught x h. Now h contains Hz, and this is the frequency part. So it will be simply written as 1 by I h cut e to the power I h t. If you write this as omega as a frequency, so this will be S naught x and Sz with this omega term, which is minus of omega term here, out. As it doesn't depend on, this commutator doesn't depend on any of these variables, right? These are constant basically. Charge is constant, magnetic field is constant, and mass is constant, and obviously the speed of light is constant. So you are left with this along with other e to the power minus I h t. Now this S naught x Sz is, or you can say the Sx Sd at time t equals to 0, right? Sx Sd is what? It is Sz as x cap with a minus sign and minus I h cut Sy. So this will give you simply minus of omega divided by I h cut e to the power I h t into I h cut minus of minus I h cut, so I h cut Sy, right, with e to the power minus of I h t, right? Now this I h cut cancels out. You are left with this thing, which is omega e to the power I h t Sy e to the power minus I h t. So you are left with what? Omega, and this is what? Time evolution operator of Sy, which is Syt. So the equation of motion will give you this: dx by dx cap x by dt equals to omega Syt. Right? So this is a simple question, but very significant, and it includes this time evolution operator, which most of the people do not think of. So remember that whenever you are solving this kind of problem, you should keep in the mind that S0 and ST are different. So you must take care of your evolution operator, right? So this is your equation. So the result is dx cap st divided by dt equals to omega x cap yt. I will better suggest you to just check into the sign more carefully, as there can be some sign discrepancy. Right? Now let us take this problem number 72, which is primarily about relation between total angular momenta and their commutation relation. So let us take it, the first one. It says that some of the two non-interacting angular momenta, J1 and J2, is given by J equals to J1 plus J2. Then which of the following commutation relations are correct? तो अगर दो नॉन इंटरैक्टिंग एंगुलर मोमेंटम्स का सम जो है वो J1 और J2 है, सॉरी J है, which where non-interacting angular momentum is J1 and J2. then which of the following commutation relations are correct? तो इनमें से कौन सा commutation relation correct है? तो चलिए पहला लेते हैं jx and jy and then we will go to others one by one. हम एक करके सभी को देखेंगे, right? So let us start with. So the first one says jx jy equals to what? So let us take the LHS for A. So jx jy, remember that it is in cyclic order. It will be simply giving you iisc multiplied by the next one. So x, y, z. So cyclic, how does the x cyclic order goes? So it goes to x, y, then z, y, z, then x, and z, x, y. So this is how it works. X, y goes to z, y, z goes to x, z, x goes to y. Now if you change the order of any of these two, the sign will change. So if you x, y goes to y, x, it will become minus z. It becomes, if z, y, y, z goes to z, y, then it goes to minus x, or similarly. So here it is jx, jy, so it is in cyclic order. ये cyclic order में है. So then what do you expect? It is simply iisc multiplied by j, z. Right? But here in the option it is given as minus iisc, so this one is not correct. So RHS not equals to RHS. Right? Not correct. Similarly, the second one also. Second one says that jy, jz, right, goes to, it is again in cyclic order, yz goes to x, so it will be iisc multiplied by jx with, but here it is minus, so it is not correct, not equals to RHS, right, so it is not correct. Right? Now let us go to this one, the third one, which says the j square and j1 square, j2 square. Right? So the C, let us take LHS. Now j is defined as j1 plus j2. Right? So j is nothing but j1 plus j2 whole square. आप इसको आसानी से यहाँ पे रख दीजिए. Just put it like that and expand it, and then take the commutator one by one. Expand करिए, then take एक करके commutator लीजिए. So it is giving you j1 square plus j2 square plus 2j1 j2. If j1 and j2 are independent, then order of multiplication doesn't matters. But if j1 and j2 are dependent, so they are operator, then their commutation will be important. So j1 j2 may not be j2 j1 in some cases. So that is the property of operator. The operators may not be commutative. They may not be abelian. But here it is, so 2 j1 j2 and j1 square. Right? Now take, as you know, that this commutator of sum of or algebraic summation of basically reduction is simply equals to commutator of each individual parts. It will be simply written as j1 square comma j1 square and then plus sign j2 square J1 square and then plus 2 J1 J2 J1 square. Now J1 square and J1 square, commutator of two same quantity is always 0. J2 and J1 are independent, as we have said very clearly, non-interacting. So O independent means in their commutator is 0. Right? Now just go to this one. If you see very clearly, carefully, the J1, now there is two possibilities. One time J1 comes out, you have a commutator between J2 and J1 square. Another time J2 goes J2 goes out, you are left with J1 and J1 square. But J1 and J1 square, they are same quantity, same variables, so it is 0. So you are left with only the other one, which is equals to 2 times J1 J2 J1 square. But again J2 and J1 are independent, as they are non-interacting, so this commutator is 0, which is equals to RHS. So as it is RHS is 0, it means this relation is correct. Right? And in the similar fashion we can prove this one also. Let us write it. So take D as J1 square J square plus J2 square as J1 plus J2 whole square J2 square. Right? Just expand it. J1 square plus J2 square plus 2 J1 J2 J2 square. Right? Now just take the commutator of each one, which is the J1 square comma J1 J2 square plus J2 square comma J2 square, then 2 J1 J2 comma J2 square. Now all of them will vanish with exactly the same region which we gave in the earlier one. So this one is also 0, which is equals to RHS. It means that this option D is correct. Right? A very important problem. This is very frequently asked in the exam. The relation between the angular momenta and then commutators, their commutator relations, right? So I hope that it will be very much helpful for you in the upcoming exams like JAM, JEST, GATE, NET, or TLF, or any other exam related to physics. Let us take this problem number 73, which says that consider a wave function psi r theta phi equals to C1 psi 1 psi N1 L1 M1 plus C2 psi 2 psi N2 L to M2, which is a combination of normalized stationary state hydrogen like wave function psi NL. Right? You know that N, L, M are nothing but the principal quantum number, L is the azimuthal quantum number, M is the magnetic quantum number. Right? So for a spherically symmetric system, the wave function is defined in this fashion with N, L, and M. It's specified, right? So for psi to be normalized, C1 and C2 must satisfy the condition. So what condition C1 and C2 must satisfy? So that the psi, which is here, is normalized. Right? Remember that psi 1 and psi 2 are already normalized, as is given. Right? Combination of normalized stationary state wave function. So let's just try to find the condition solution. Basically relation between C1 and C2. So if it is normalized, then psi r theta phi, the inner product must be unity. right? That is the normalized means, right? So, right? But what is this? This is C1 psi N1 L1 M1, right? Plus to just multiply the two, you will find that it is giving you so C1 star will be from here. Remember that psi1 and psi2 are normalized, so their inner product will be 0. So we are considering them their inner product. That's why we are taking the cross terms, right? So only terms like this is taken: psi n1 l1 m1, psi n1 l1 m1 plus c2 star c2 psi n2 l2 m2 psi n2 l2 m2 equals 1, right? Now this is, as they are normalized, this is unity and this is also unity, right? So what exactly you are left with is, this is C1 star, C1 is mod C1 square plus C2 star, C2 is mod C2 square, which is equals to 1. So this is the condition which C1 and C2 must satisfy to get a normalized wave function psi or theta for you, right? So simple and but very significant problem, particularly for exams like GATE or any PhD entrance exam. It's a one-line problem, one or two-line problem, but a little bit of awareness is required how you can smartly solve it, right? So hope this particular example will be helpful to you in tackling these kind of problems. So please note it down, and if you have any query, please write in the comment section. Hey everyone, let us take another important problem. It says that at time t equals to 0, the wave function of the hydrogen atom is psi r0, which is equals to 1 by root 10 2 psi 100 plus psi 210 plus root 2 psi 211 plus root 3 psi 21 minus 1, where subscripts are the values of the quantum numbers L and M. So subscript is N, L, M. So here this is N is 0, 1, M is, L is 0, M is 0, similarly like that, right? So the expectation value of the energy of the system is what, right? So let us try to calculate that expectation value. So you know that the formula for expectation value is what? It says that psi r0 h cap psi r0, right? So it will have two parts. So when you multiply, it will give you 1 by root 10 multiplied by 1 by root 10 as 1 by 10 right? Now psi has two parts. The 1, 0, 0 part is basically the wave function of the ground state, and this part is basically the wave function of the first excited state. Right? So this is 1 as 0, this is 1p. The 1 as state, 1p state, right? Where S has L0 and M as 0 and 1s. This is 2p. 2p, L equals to 1, L equals to 1, L equals to 1, M0, 1 minus 1. Right? So this is psi so 2 psi 1 0 0 H cap 2 psi 1 0 0 as the states are orthonormal to each other. Right? Plus 1 by 10 psi 210 H psi 210 plus 1 by 10 into root 2 psi 211 H root 2 psi 11211. Right? Where root 2 will be coming out giving a 2. Similarly, 1 by 10 into root 3 psi 21 minus 1 H root 3 psi 21 minus 1. Now let us simplify it. So when you simplify, this will give you expectation value of H in the ground state is E1, right? So this will give you E1, and this will give you E2, E2 and E2, right? So just simplify it. So this is giving you, this 2 is coming out, giving you 4 by 10 into E1, 2 multiplied by 2. This is giving you 1 by 10 E2. So just simply write it, 4 by 10 E1 plus 1 by 10 E2 plus here root 2 and root 2 coming out is 2 by 10 E2. This is second stage, then root 3 and root 3 and 3 by 10 E2, giving you 1 by 10 plus 2 by 10 plus 3 by 10 is 6 by 10 E2 and 4 by 10 E1. So 4 by 10 E1 plus 6 by 10 E2, right? So let us write it more clearly. So its expectation value will be nothing but 4 by 10 E1 plus 6 by 10 E2, where E1 is the energy of the ground state and first excited state E1, E2, right? So this is how you can find the expectation value of energy if a wave function is given defining a particular state, right? It is given that it is at time t equals to 0. So that's why we are not considering time anywhere, R0, right? A very significant, very important and significant problem. So please note it down and solve. It will be helpful for you in tackling other similar kind of problems, right? So please note it down. Now let us take this important problem about the angular momentum. It says that kits J, M are the simultaneous eigenkits of total angular momentum operator J square and its jet component Jz with eigenvalues at J plus 1 h cut square and m h cut respectively. Then J plus and J minus are eigenkits of J square. It is asked that whether they are eigenkits of J square with same eigenvalue. So let us try to solve this problem and try to understand whether J plus and J minus are eigenkits of J square with same eigenvalue. So you know that J square operating on J comma M gives you J plus 1 h cut square, right? And then Jz right? Now they are simultaneous eigenkits. It means that if two operators are simultaneous eigenkit, if a big function is simultaneous eigenvector of two given operators, then the operators are commutative. So it's a very important problem, right? So it means that if they are simultaneous eigenkit with eigen, it means that J square and Jz will commute. Right? It means this. So you can check it whether it is true. J square is Jx square plus Jy square plus Jz square, right? Plus other terms. And when you simplify and try to find the commutator, you will find this is going to be 0. Right? So, now let us try to find J plus and J minus and the relation with J square. So how does the J square and J plus work? Right? So J square is the total angular momentum operator and J plus is Jx plus Jy, Ijy, obviously, right? And similarly J square with J minus. J square Gx minus Ijy. Right? Now if you solve this, you will simply find that J square Jx comma plus I J square Jy. So J square will basically vanish with Jx and Jy also. So this is giving you, similarly this one is also going to be giving you J. So if these are operators which are commutative, it means J square commutes with J plus, J square commutes with J minus. Right? It means the J square operating on some state j comma m is equivalent to saying that j plus j square j comma m. Right? But j square operating on j comma m gives you nothing but j plus and j plus 1 h cut square. It means that you are left with j plus 1 h cut square into j plus j comma m. Right? Similarly, j square, j minus operating on this will give you j plus 1 h cut square j minus j comma m. So this acts as an eigenkette for the operator j square eigenkette. Here also it is eigenkette with eigenvalue as this eigenkette. So if two operators are commutative, then they can act as, they can be written as an eigenvector can be written as the simultaneous eigenvector of the two operators, right? So using that theorem, property, we have just proved that j plus and j minus with act as a simultaneous, basically act as a simultaneous eigenkette of j square. Act as an eigenkette of j square with eigenvalue j plus 1 h cut square. Right? This is something very significant problem, and which is particularly important. That it signifies one of the most important properties of operators. Right? The two operators are if they are simultaneous eigenvectors of a single simultaneous operator of so they are basically operators correspond whose eigenkettes are same, or basically they simultaneous, then they are commutative in the nature. Right? So these two operators are there which have same eigenkette, so they are commutative in the nature. Similarly here also these two operators are there, they are commutative, so they have same eigenstate. So it can be vice versa. If they are commutative, then they have same eigenstate. If they have same eigenstate, simultaneous eigenstate, then they are commutative. So both are true, right? So please remember this. So this is all we have in today's lecture, where we discussed 5 very important problems on angular momentum. So these problems are going to be very much helpful to you. So please go through them and try to understand and revise it and try to solve similar problems based on this.